Hi, so we will have the practice about alignments, starting with pairwise alignments. Pairwise alignments are scheduled for lesson number 4, and in here we will present how to perform the pairwise alignments using graphical or alignment tools. So for that, you can get the supporting materials at lesson number 4, and you will get the 2 sequences that are available to perform pairwise alignment, TBP1 and TBP2. You can download them and get them in order to perform the pairwise alignments. One of the softwares that are available to perform pairwise alignments using 2 sequences, it's a graphical alignment. The graphical alignment can be performed using Dotplot. Dotplot is available on several platforms. One of them is suggested on your exercise 3, and you only need to input your sequences. Then you will input each sequence, naming TBP1, and then you transfer your sequence here, TBP1, to use this. You really need to have Java installed in order to use this tool called Dotplot. Now you will place this next sequence, TBP2, and then you transfer your TBP sequence here. And as long as you get the 2 sequences, Dotplot will allow you to perform a graphical view of what is corresponding between the 2 sequences. So what you have is that you can perform the alignment between TBP1 with TBP2. In the beginning, you can leave the parameters as it is. The size of the window, it can be higher from lower 1 until 59. Also, you can leave the sequences 1 for 1. Only if they have different sizes that you will select here a different parameter. And now you can compute and get the result of the alignment, and you have a lot of the sequences corresponding that shows with white lines. So you can check that in the beginning, where both sequences begin, you have high conservation between the 2 sequences, and then you have one other small area of high conservation, that is here. If you change the zoom into 1 to 3 and then compute, you can check zooming out and see almost all the sequence once. Now you can check the parameters you have on horizontal, the TBP1, vertical you have the TBP2, then you have identity to find what is identical, so the corresponding and exactly corresponding nucleotides once you are comparing the 2 transcripts. The sliding window is 59, so it has a little background and little noise. And finally you have a zoom 1, 2, 3. As you can check in your graph, you can see that you have a corresponding between both in the beginning, exactly the same nucleotide sequence, and then you have a gap, an horizontal gap. So the sequence that is on horizontal is much longer than the vertical one. The horizontal have this piece of sequence that the vertical sequence don't have. Then you have, once again, all these identical nucleotide sequence until the end. As you can see here, this square, it means that you have repeats. So what we have here, it's a repetition of a triplet of something that you cannot check. So you know that has some identity in the beginning, in the end. You have a gap, so they have different sizes, but you don't know where the gaps is placed. You don't know the number of the nucleotide, and you can see the nucleotides repeated here. So for this graphical alignment is very useful. For example, to see repeated domains, conserved domains, and you can check also the introns and exons, comparing a gene with its transcript. So in here you could check that has 3-4 exons, that is the sequence that is corresponding from gene into the transcript, the cDNA. You can see also frame shifts, if there is a shift between the sequences, and also check low complexity regions. As you can see here, there is a low complexity region similar to what you got in your results. So there is a repeat of a certain amino acid that in the transcript corresponds to the codons that are repeated along a certain size region. So which codons are they? Where the sequence really align. How can we check that? We can check that performing a pairwise alignment. And this kind of pairwise alignment can be performed using LAlign software. LAlign allows you to perform pairwise alignment using only 2 sequences, the first sequence, second sequence, and you can perform local alignment that will only show you what is aligned, a global alignment that forces the alignment of the 2 sequences from the beginning until the end, so it's more used in sequences with the same size. Or you can get a global alignment without end gap penalty. So if there is no alignment in the ends of the sequences, it won't show you. So it's not a perfect global alignment. The default is a local alignment. You may get several alignments as result. You can use different score matrices, either point accepted mutations or blocks substitution matrix. The default is Blossom 50, but you can use Blossom 62 because you know these sequences are quite similar. The transcripts you're using, TBP1 and TBP2, you may use the default gap opening penalty and gap extension penalty. And then you can place the sequences, the same 2 sequences. So the second one was TBP2, and you have in memory still TBP2, and you will get once again TBP1 sequence. You have to name it TBP1, and you can run your alignment. And in here, as a result, you expect to have the alignment. Here you can see all the parameters chosen, okay, the matrix, opening and extension penalties, the size of your sequences, okay, TBP1 and the second sequence, also TBP2, and finally you have the score calculated based on Waterman-Heger, that is the algorithm for local alignment, and you can check that they have 89.5% of identity and an E-score of 3.2. Now you can check that TBP1 is higher, has a sequence that TBP2 don't have, and TBP2 shows the gaps from 133 nucleotides around until 330 something. Then you have once again perfectly identical, so it's the 89.5% identity that you have in here until the end of the sequences. And you can check, if you ask more than one alignment, you will get the 3 proposals. Now you're watching the first and the better alignment proposal. The 2 dots, it's representing the identity. Different applications, different softwares design may represent differently your identity and similarity according to conservative or not conservative. If you change your parameters like gap opening extension and gap opening and gap extension, you may get a different score. If you increase the numbers of gap opening and gap extension, you will get a lower score because it is subtracted. Most softwares represented with a minus, although gap opening and gap extension are positive values. If you change your score matrix, the substitution matrix that you have in here as Blossom 62, you may also get different results. So you should really keep your values in order to compare your results. So you have 2 sequences. You may compare them using Dotplot just to get a graphical result, or you may use LAlign to perform a pairwise alignment where you can check where the sequences are identical, where the sequences are different, and you really can check the region that you have with repetitions. Here it is. You have always the same triplet that will show up as an amino acid, a glutamine amino acid. Now you will have to do this in exercise number 3, following the instructions. Thanks for your attention. Meet you soon in the theoretical and other practical classes. Thanks for your attention. Bye now.